This is a reminder, class connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please do not share personal information. Yes, Haley, definitely take time over the weekend to get better. All right, today we are on the October 5th ticket, so go ahead, open that up, please, and give me a green check when you have that open. All right, so it's in the chat box right now. Make sure you spell it correctly, make sure you capitalize it correctly, get that opened and ready to go. There are only 16 days left of the quarter. It's ending super soon, so make sure that you are on top of everything, getting your work done. Today we do have an extra credit game day. We're going to have to do it a little bit differently because Blackboard Collaborate is not cooperating and not letting me share my screen. So we're going to figure out how to do it a little bit differently, but you will still get credit as long as you do your best and participate. Smiley faces if that makes sense. We will have to do it a little bit differently, but we will get it done. Awesome. All right. So we are talking about work. Work is what we looked at this unit. So we talked about simple machines, we talked about work and power, we talked about pulleys and levers. So there's a lot of stuff that we went over this week. So the first thing is, remember, we talked about work, and the equation for work was force times distance, because the definition of work is a force applied to an object over a certain distance, or displacement, right? You could say the displacement as well. That's the same word, right? This could also be displacement. Okay, so for example, we took a look at this problem. Let's review this problem again. If we push a box 15 meters along the ground with a force of 100 newtons, we want to know how much work is done, right? So if we've got work equals force times distance, so work equals force times distance, tell me in the chat box, what do I plug in for my force? What do I plug in for my force? Jeremy, if you go ahead and email me, I can get back to you on that, but I don't have time to look at it right now. Our force, yes, is going to be the one with newtons, so 100 newtons, yes, times our distance. What should our distance be? What should the distance be? Yeah, 15 meters. And then tell me in the chat box, what is 100 times 15? What is my total work here? No, none of those are correct yet. None of those are correct. Yeah, okay, now we're getting it. We're missing some zeros. We had too many zeros. Let's make sure we get this. Yeah, so this is going to be 1,500. And the units for work, remember, are actually joules. 1,500 joules. Smiley faces if that makes sense. Okay, again, the way that we find work is we just multiply the two numbers, force and distance. Now, the important thing, though, is that, again, when you're looking at whether or not there is work done, A, there needs to be a force. B, there needs to be a displacement, and C, they have to be parallel to each other. Remember, parallel lines, do they look like this or do they look like this? Do they look like this first picture I just drew or the second one? Parallel lines, which one is which? The first picture or the second picture? Yes, exactly. So when we talk about parallel lines, they have to be parallel to each other. Force and displacement have to be parallel. So for example, right here, taking a look at this person who his force is upwards because he's holding a box up, but he's walking to the right. Are those things parallel? Are these things parallel? If his force is upwards, but his displacement is to the right? No, they are not parallel, right? These are actually perpendicular to each other. So if they're not parallel, has he done any work? If they're not parallel, has he done any work? No, therefore no work. Exactly. What about down here? Again, we can see this person, he's pushing on the box, but there is no displacement. Is there work done here? Again, take a look at our three things. There has to be a force, there has to be a displacement, they have to be parallel. In this situation here, is there work being done? Okay, tell me, is there a force in this picture? Is there a force in this picture? Yes, there's a force. Is there a displacement? Is the object moving? No. So if there is no displacement, is there any work? Okay, we have a force, but no displacement. So therefore, is there any work? No, exactly. So here, there is no displacement, there's no movement, and therefore there is no work. Okay, smiley faces if that makes sense. Smiley faces if that one makes sense. Awesome. And then our last one here, we can see there's a force pulling this guy to the right and he's moving to the right. Is there work here? Is there work here? Again, look at all three things. Is there force? Is there displacement? Are they parallel? Yeah, absolutely. We can definitely see a force and we can definitely see a displacement. And we know that they're parallel and therefore there is work. All right, give me a thumbs up if this makes sense. All of this information about work that we've been looking at throughout this unit. Perfect. Okay, guys. So here's the next thing. Remember that we also talked about power, and work and power are related to each other, but they're not the same thing. Remember, work is just the force over a certain amount of distance. Okay, so this is actually always the same in every situation. Work is always the same because you always have to use the same amount of force over the same distance to move an object. Smiley faces if that makes sense. Work is always going to be the same. Work is always going to be the same. Okay, however, power can actually change because power is actually the rate at which we do this work, meaning power includes time. Work does not include time. Work, it does not matter how long you take, the work will always be the same. Power, though, time matters. So if you decrease the amount of time, you are actually more powerful. Remember, think about having to do a bunch of work. If you can do all of your work in 1 hour as opposed to somebody else who does all that work over an entire day, you are more powerful, right? You're going to get a promotion faster than the other person. So if you decrease the amount of time it takes you to do work, you are more powerful. If you increase the time, then you're less powerful. So again, in this situation, for example, these bikers are both doing the same amount of work. To get to the top of hill, in total, you have to do the same amount of work. But they're going to have different power because it takes them different amounts of time. Who do you think has more power, A or B? Who do you think has more power, A or B? A takes 30 seconds, B takes 45 seconds. Who's going to have more power? Yes, A is going to have more power, right? It takes him less time to get to the top of the hill, and therefore he is more powerful. Smiley faces if that makes sense. Smiley faces if that makes sense. The less time you take, the more powerful you are. Excellent. This is number 1. Give me a green check when you have this saved. Just waiting on Adrian, Andrew. Let's see here. Dalen, Dolly, Jacob, Melissa, Tyson, Zoe O. Green checks, please, if we're good on number 1. Looking good. Let's keep on moving. Okay, so let's review really quickly simple machines, right? We talked about all these different simple machines, right? Here's a wedge, here's a lever, here's a screw. We see a wheel and axle here, an inclined plane here, and a pulley right here. Grab your whiteboard tools, match these up to their definitions. Remember, read them all carefully. Some of them use similar terms, but they're not the same thing, so read them carefully. Go ahead, get your answers up there. You guys have 30 seconds. Ready, set, go. All right, let me go ahead and pause your tools here. Let's go over our answers. A little bit messy, but we'll clean it up. All right, so looking at this, yes, a wedge is when we have 2 inclined planes back to back that are used for cutting. A lever is when we have an arm or a board that pivots on a fulcrum. Screw is an inclined plane that encircles a central rod, right? If this is our screw, that plane goes around and around, encircling our rod here. A wheel and axle, let me change colors so it's not as messy. Wheel and axle is when we have a wheel with a post through its center. Inclined plane is just any slanted surface. And a pulley is going to be when we have a rope wrapped around a wheel. Give yourself a round of applause. Oops, not a confusion face. A round of applause. Good job on this one. Awesome, looking good. All right, guys. So of those simple machines, we spent a lot of time talking about levers. So remember, levers rotate on a fulcrum, right? The point at which they pivot, that is what's called the fulcrum. And we saw that with lighter objects, in order to balance a heavy object, do they need to be closer or further away from the fulcrum? Remember, this was our experiment yesterday. A lighter object, does it need to be closer or further away than the heavy object? Yeah, it needs to be a lot further away. So we saw that if we use a longer distance, you can actually lift a heavy object with much less force. So you could actually lift up an elephant if you had a long enough arm where you could be far, far away from the fulcrum. Smiley faces if that makes sense. You yourself, as a human being, could lift something up as big as an elephant if you could be far enough away from the fulcrum. Yeah, so bigger distances, less force makes it easier. Now, this idea of making it easier, this occurs with both levers and pulleys. And what levers and pulleys do is they increase what we call mechanical advantage. Advantage meaning like a good thing. So mechanical advantage, increasing it actually makes it easier. It means we're making it easier. So remember that on either side of a pulley or either side of a lever, it's still exactly the same work, right? Because you can't change the amount of work you do in order to lift an object. But on one side, we can use less force, and therefore it feels easier. Smiley faces, if that makes sense. It's always the same amount of work, but we can make it feel easier by using less force. Now, the only way that we can use less force is by actually being further away, just like we learned right here with this little kid, right? The only reason he can lift up this big guy is because he's further away, so he's offsetting his smaller force by using a bigger distance. And we saw this right here, right? Remember, work equals force times distance. So really quickly, what is the work that our guy is doing right here in this picture? Force times distance. What's 10 times 5? Tell me in the chat box. What's 10 times 5? Yeah, 50. And remember, our units for work are joules, so 50 joules. And on the other side, if I didn't have the pulley, I would have to lift a 25 Newton object up 2 meters. And what would that work be? In order to lift up a 25 Newton object 2 meters, what would that work be? On the other side. 25 times 2, 25 times 2, force times distance. Yeah, it's actually exactly the same, right? So again, this is proving to us that no matter what, work is always going to be the same, whether you're on the easy side or the hard side. Okay, now looking at this, guys, which side is easier? The side with less force or the side with more force? The side with less force or the side with more force? Yeah, absolutely, the side with less force, right? So here we have less force, but we're offsetting it with more distance. On the other side, we'd have to use more force in order to lift something up with less distance, okay? And so what we find is, again, the side with less force, that is our easy side. Smiley faces if that makes sense to you. Smiley faces if that makes sense to you. We learned a whole lot about these always being opposite from each other. Excellent. This is number 2. Give me a green check when you have number 2 saved. You have 30 seconds. Ready, set, go. Just waiting on Eric, Jacob, Jasmine, Melissa, Michael, Seha, and Siva. Yes, we're going to play Kahoot today. We'll see how well it works because my computer, my Blackboard is not letting me screen share, so we're going to have to do it a slightly different way, but we will do it. All right, so here's the thing, guys. We talked about how levers and pulleys, right, these increase mechanical advantage. They make life easier for us when we lift up heavy objects. However, we also took a look at a bike, and a bike actually uses simple machines to decrease mechanical advantage, making it harder for us, right? We talked about how pedals require a large force to get them moving, so much so that a lot of times when we're biking, we actually start by standing up so that we can get enough force to move those pedals. Smiley faces if you remember that, okay? These take a very large force. This is actually much harder for us. Okay, but the result is that on the opposite side of our simple machine, the back wheel, what ends up happening on that is that it actually does the opposite. So the back wheel doesn't use a large force, it uses a small force, but the result is it gets a very, very large distance. And if you can move a tire a large distance in a small amount of time, this gives you more speed. Okay, so the whole purpose of decreasing mechanical advantage is so that we can get more speed. Smiley faces if that makes sense. The only reason we make it harder for us is so that we can get more speed and go faster. Excellent. Looking good. Okay, so let's go ahead. What you're going to do, you're going to go to kahoot.it. You're going to go either on your phone or a computer browser. Once I show you the pin, I'm going to have you enter it. And then you'll enter your real name, first name, last initial. Please don't use anything inappropriate. Please don't use your full last name just for security reasons. And then we should be ready to play. Now here's the thing, guys. Again, my computer is not letting me share the actual screen with you. I mean, I can try it again, but yeah, application sharing is not working for some reason in Blackboard today. So what we're going to do instead is I'm going to actually paste the question on the whiteboard. It's going to take a few moments to load, but as soon as it loads, after it loads, I'm going to give you 30 more seconds to answer it. Okay, smiley faces if that makes sense. So it takes a few moments to load. I'm sorry about that, but as soon as it loads, you'll have 30 seconds and then we'll move on to the next one. Okay. All right. So let me go ahead. Remember, you get extra credit just by participating. So if you're not sure, just answer it anyways. You'll still get full credit as long as you are answering the questions. But obviously do your best. And then extra credit, if you're watching the recording, is only during the live session. There can't be any exceptions just because it is a game. No, you can use Mike W. That's totally fine, Michael. Sorry, Mike, obviously. All right, so here we go. I'm going to go ahead and here's our page right here. And then I'm going to go ahead and play this. Give me a moment to get it started. All right, guys, so here is the pin. Sorry, let me get it on the whiteboard there. There's the pin for you. Go ahead, log in, please. Gonna make this a little bit smaller. Excellent, looking good. I have 10 players so far. 13. No worries, Dolly. Here you go. Dolly, I just opened a private chat for you, so type your answers in the private chat so other people can't see your answers. Perfect. All right, I got 18 people so far. All right, looking good. All right, how many of you are there? There's 35 of you. I have 25 people so far. Go ahead, get logged in, guys. Try to get all your players in here. And then I'm going to start in about 20 seconds. Start in about 20 seconds. Yes, it did, Ariana. The cat, the heart, and the pumpkin. Yeah, Zoe, the only thing you can see right now is the pin because I can't share my screen right now. Blackboard is not letting me share the screen, so I'm just pasting it on here. Awesome, guys. All right, let's go ahead and get started. So let me go ahead and grab a picture of this. Give me a moment. Oops, sorry, hold on. All right, here we go. Lines that will never intersect are what? Go ahead and answer that one. It should be loading in a few moments. No worries. Here you go, Jasmine. I know, Annalise, I'm sorry. Your computer is super slow. Sorry, Ariana, it's totally fine. Go ahead and in the chat box, I'll open a private chat for you, and you can answer in the private chat. So the question was, lines that never intersect are what? Both, parallel, neither, or perpendicular. Awesome, guys, looking good. So it looks like we answered parallel, and parallel is definitely correct. So let me go ahead and make sure that that makes sense. Edgar's in the lead. Grant is following. Let's go ahead. Give me a moment to make sure this makes sense. I'm going to copy this and paste it on the board. All right. So remember we saw here that when we have intersecting lines, all right, that's when they cross each other. If they never cross each other, that's parallel. And if they cross each other at a right angle, that's perpendicular. Right, let me know if that makes sense. Go ahead and answer. I know, I'm sorry, Ariana. It's all good. It's totally the computer's fault. So you know you can blame it on the computer, right? Not your fault. Awesome, looking good, guys. Get your answers in there. Give you about 10 more seconds. And then I'm going to go ahead and keep on moving. Bad computer, seriously. All right, let's go ahead and keep on going. Looking good. All right, next one. Let's go ahead. What is the equation for work? So equation for work, I'm going to go ahead, paste this on the board. Give me a second. Equation for work. What is the equation for work? Go ahead, answer that one once it loads. Give it a few moments. Come on, computer, work faster. There we go. It should be loading for most of you. Sorry, Ariana, it's still messing with you. But Ariana, the options are force divided by distance, force times distance, force minus distance, or force plus distance. Go ahead and answer in the private chat, and I can give you credit for that, okay? Looking good. Awesome, Dolly. I see yours. I know, Ariana, I just told you the possible answers. So go ahead in the private chat. You'll answer in the private chat, okay? Awesome. No worries, Miranda. Thank you. Yes, work is going to equal force times distance. Force times distance. All right. So we've got, sorry. Next one is, which of the following is not a requirement for work? Which of the following is not a requirement for work? All right, go ahead, answer that one. Again, it should be loaded in a little bit. I know, Ariana, it's so sad. Okay, so which of the following is not a requirement for work? Ariana, your options are time, motion is parallel, force, or displacement. Okay, Zoe, you can answer in a private chat. Okay, so I just opened up a private chat for you. Which of the following is not a requirement for work? Time, force, motion is parallel, or displacement? Go ahead and answer in your private chat. I know, marvel, right? Looking good. Okay, awesome, Ariana. Yes, Dalen, that's fine. I know. What's up with that? All right, so not a requirement for work is actually going to be time. So let's make sure that this makes sense. Time is actually the correct answer. All right, because remember, we learned that work only requires force and distance or displacement, and it requires that that displacement is parallel. All right, let me know if that makes sense. Go ahead, get that up there. Yeah, Dalen, as long as you answer in the private chat, you'll still get your credit. Looking good, looking good. 10 seconds. Then I'm going to keep on moving. 3, 2, 1. All right, looking good. Awesome. Edgar in the lead. Mike is following. A person pushes a box 6 meters along the ground using a force of 2 newtons. What does work equal? All right, so 6 meters, 2 newtons. And remember, our equation for work is force times distance. Force times distance. I know, computer, come on. So 6 meters, 2 newtons, work equals force times distance. What should be our answer here? Looking good. I got Zoe O's answer, Dalen, Miranda, and let's see here, Ariana. Make sure I get yours in the private chat. Awesome. Thank you, Dali. I see yours. 10 seconds. 3, 2, 1. Good. All right. This should actually be 12 joules. Our answer here is actually 12 joules. All right. Mike is in the lead. Michael R. is following. And the next question is work being done? So here we go. I'm going to go ahead, send this to you. Is work being done? Oh, good job, Ariana. So we can see we are applying a force upwards and we are moving to the right. Is work being done? Yes or no? The triangle is yes, the diamond is no, Ariana. Triangle is yes, the diamond is no. If we are pushing upwards but moving to the right, is work being done? Looking good. Awesome, Dolly, I got yours. Zoe, Miranda, Dalen, make sure I get yours as well. Yeah, looking good. All right, 10 seconds, everyone. Oh, it's working. Awesome, Zoe. All right, the answer here should actually be no. The answer here is no. Why is work not being done here, guys? Why is work not being done here? The force and the displacement are what? The force and the displacement are what? They are not what? Yeah, they're not parallel. They're actually not parallel. Okay, if they are not parallel, then work is not being done. Smiley faces if that makes sense. Smiley faces if that makes sense. Awesome. All right, the next one also asks, is work being done? This time, we have a force with no motion. A force with no motion. All right, should be on the board in a moment. All right, red yes, blue no. Red yes, blue no. Is work being done? If we have a force without motion. Awesome, Miranda. I see yours. If you're not sure, just do your best. Just guess. It's all good. It's all good. Just do your best, guys. I know, the struggle is real today. This is so frustrating. I need to figure out why my Blackboard won't let me app share. All right, awesome, Dalen. I see your answer. Ariana, you're such a good sport. 10 seconds. You got this. Oh, interesting, Annalise. Oh no, Angelina. It's okay. We can catch up. All right. So in this case, work again is actually not being done. Can anyone tell me why work is not being done? All right, we've got Mike W in the lead. We've got Andrew following closely. Zoe is up 5 places, climbing high. Why is work not being done here? Yeah, there's no motion. There has to be motion or displacement in order for work to be done. Excellent. So that being said, let's make sure that this makes sense. Give me a moment. Red, yes. Blue, no. Or sorry, blue, a little. And yellow, not at all. Does this make sense, right? In order for work to happen, there has to be a force, there has to be motion or displacement, and they have to be parallel. All right, red, yes, blue, a little, yellow, not at all. It's okay, Ariana. I feel like you would probably be doing much better if you could actually see the screen like I can. All right, 10 seconds, everyone. Get me your answer here. Yes, that's true. But you don't actually get points for this one. But yes, all answers are fine. All right, I'm going to go ahead and keep on moving. Answer now, 3, 2, 1. Looking good. All right. Next one, Mike is in the lead. Andrew is now closely following. Which of the following is true? Which of the following is true? All right, so this is about work versus power with our two bikers. Okay, are work and power the same? That's your red option. Is work the same but power is different? That's your blue option. Work is different and power is different. That's your yellow option. And then work is different but power is the same. That's your green option. Taking a look at our biker here. Think about the difference between work and power. Remember, power includes time. Power includes time. 20 seconds left. Work quickly. If you're not sure, just guess. If you're not sure, just guess. Awesome, Miranda, Dolly, I see your answer. 5 seconds. Click, click, click. Come on. All right, in this case, work is actually the same, but power is different. Work is actually the same, but power is different. Ariana, you're the highest climber. Mike is still in the lead. So that being said, which of these has more power? Which of these has more power? Red is person B, blue is person A, and yellow is neither. All right, which of these two bikers have more power? The one that takes 30 seconds, that's the blue option. The one that takes 45 seconds, that's the red option, or neither. I don't know, Ariana. I can't actually see your places. You can see your places. Awesome, Miranda, Dolly, I see your answers. Thank you. All right, let's take 10 more seconds. Get your answers up there. This question, oh, sorry. Which person has more power? More power. The one who takes 30 seconds or the one who takes 45 seconds to get to the top of the hill? Who's got more power? Oh, Haley, don't write your answers in the public chat. If you need, I can, oh, thank you. I see you're just helping her out. No worries. Yeah, so in this case, letter A, the blue one actually has more power because that person does it in less time. Vega is on a streak. I like it. So that being said, if we want to increase power, what do we actually need to do to the time? All right, your options are red, increase the time, or blue, decrease the time. If we want to make it more powerful, do we need to increase or decrease time? Increase is red, decrease is blue. All right, should be on the board soon, except for Ariana, because the computer doesn't like Ariana. There we go. Now it should be up. Do you see it, Ariana? There you go. To increase power, to become more powerful, do we need more time or less time to do the same amount of work? Does it need to take us more time or less time to do the same amount of work? Awesome, I got Miranda's answer. Dolly, make sure I get yours. 10 seconds. Awesome, thank you, Dalen, I see yours. All right, in this case, we actually need to decrease the amount of time, right? The faster you can do it, the more power you have. Andrew in the lead, Vega following. So let's make sure that this makes sense. All right, let's make sure that this makes sense. Red is a little, blue is yes, and yellow is not at all. All right, so again, power is the rate at which we do work. So work always stays the same. It's just that more power means you're speeding it up. So to increase power, we actually need to decrease the amount of time. We need to do it faster. Smiley faces, oh, sorry, no. Answer the question if that makes sense. Answer the question if that makes sense. Red is a little, blue is yes, yellow is not at all. There we go, everyone. Let's take 10 more seconds to do this one. Answer quickly. 3, 2, 1. And looking good. All right. Andrew's in the lead, Vega following, Mike not far behind. The Archimedes pump is an example of which simple machine? Red is wheel and axle, blue is screw, yellow is pulley, and green is lever. The Archimedes water pump that we saw a video of is that wheel and axle red, screw blue, pulley yellow, or lever green. You can see this top 5 people, right? So Ariana, that means everybody's in 6th place at least, right? So you can always say that you're in 6th place because who's going to know, right? Awesome. Miranda, I see your answer. Dalen, Dolly, make sure I get yours. Yeah, Haley, that's fine. I see. No, Kim. All right, looking good. Zoe, oh, I see yours. Sorry, I'm going to write down your names really quickly so I make sure everyone gets their credit. Perfect. All right, looking good. The answer here was actually screw. The answer is screw. This is an example of a screw. Edgar, you are on an answer streak. Next question is to lift a heavy object. I need to be where to the fulcrum? Red is closer to, blue is further from. To lift a heavy object more easily, I need to be what to the fulcrum? Closer, that's red, or further, that's blue. Closer red, further blue. Awesome, Miranda, I see your answer. Dolly, Dalen, Zoe-O, and Haley, make sure I get your answers as well. Awesome, Dolly, I see yours. This is going to be our last question, guys, so that we can go ahead and finish this up. All right, 10 seconds left. Awesome, Haley, I see your answer. Zoe, Dalen, make sure if you didn't answer on the game that you answer in the chat. Awesome, I see both of yours. Perfect. All right, looking good. And the answer, you guys, is further from the fulcrum. All right, remember the reason is because if you want to use less force, you always have to have more distance. All right, sorry, I'm going to go ahead and skip through these. Here we go, though. Let me go ahead and go back to your last word of the day, and I will see you all later. Thank you, everyone. Have a wonderful day. Bye. Sorry it was so messy, guys, but we got through it anyways. See you later. Bye, Sam.